New York City plans to reduce carbon emissions by 90% by 2050. In order to achieve this goal, public schools need to transition from gas heating systems to electric heating systems. The school you see in front of you right now is IS 429, an intermediate school in Sunnyside, Queens. Our goal is to design the electric heating system that can operate even on the coldest days, which is estimated to be about 10 degrees Fahrenheit. The cost of heating must also be 10% lower than the current cost using natural gases. Here you can see a model of our school built in AutoCAD Fusion 360. There isn't a need to tear down most of the existing infrastructure because our design builds on top of the existing ones. We use the same ductwork system with a few minor changes: air handling units, generator, and chiller. The main changes we made were adding in 7 American Standard Voyager heating units for the air heating and cooling system and A.O. Smith DVE 500N for the water heating and cooling system.
For the final design of our prototype, it was important for us to model it on CAD to get an initial idea of the subsystems and how they would all connect into a control volume, as well as sizes and measurements. It was also important to research and search for real tools and parts that can be used. With both of these in mind, we came to the conclusion that sizing the school model to roughly a 1 to 100 scale to about a 2 feet by 1 foot by 1 foot box would provide the sufficient surface area and volume to display the heating and cooling performances desired. This allowed for the sizing of the components connected to the box and determination or feasibility for several ideas. For example, the first idea of having a door open on the front couldn't service things easily, which is why we chose to have a lid on top instead. However, ideas like a 4-inch exhaust fan or duct, or 0.5-inch pipes on the side of the box worked well, as there was enough surface area on both sides. As part of the air heating system, a Honeywell heater was used to flow heat through a duct into the control volume. However, inside the Honeywell heater, there is a 4-inch fan that blows the heated air through the outlet. This particular outlet has a specific surface from which air can escape. My objective here is to design a connection for that heated air to flow into the duct that leads to the control volume. This issue can be solved by designing and 3D printing a cover onto the heater that enables the air to be closed while keeping it insulated to enable the most optimal flow into the duct. This leads to the cover that I designed here. As you can see, the cover funnels into a 4-inch diameter circle that is meant to connect to the duct. The reason why it is enclosed this way is to make sure that no air escapes and the flow is directed in through the duct.
This footage shows the fully assembled prototype collecting data. On this end of the box, you can see the hot and cold air systems. We have a duct fan, which is used for bringing cold outside air into the system, along with a Honeywell heater, which will pump warm air through a 3D printed part into a duct and ultimately into the control volume. As we walk around the box, you'll notice there's the hot water system at the other end. This takes warm water, pumps it through a PEX piping system, which will radiate into the box. We can set the water temperature to be anything we want, and in this case, 40 degrees Celsius was used. The water system is powered by a pump. This pump is powered by a solar cell and a battery pack. Here you can see the temperature controller. This turns on and off the hot and cold water systems. It's currently set to 70 degrees F and is reading a temperature of 68 degrees. We have another temperature probe which reads data to the laptop you're seeing here, and this is powered through an Arduino. After this, we'll go cover each subsystem in greater detail and explain how the system works successfully.
Let's talk about the air heating and cooling system. Since we weren't able to find a small heat pump that fits within our budget, we substituted it with a small resistant heating unit, the Honeywell heater, combined with a cooling fan system. What we liked about this unit is the flexibility to choose multiple power levels. You can see that it is connected to the control volume through a custom 3D printed part and ductwork. The hot air will get circulated throughout the school, and the duct fan is used to bring the cool air into the control volume. These systems will work in sync to keep the control volume at a steady temperature that we set. The duct fan is inferior to an AC unit because it can't cool below the outside temperature, but it is cost effective for the sake of this prototype. This demonstrates what will ideally happen for a system large enough for the school.
Let's take a better look at the water heating subsystem. You may notice it's composed of a water heater, pump, PEX tubing, and various adapters. Flow goes out the red tube when it's hot, through the PEX system where it radiates to the control volume, then it flows into the pump and back to the water heater through the blue tube. Here we can see the control screen of the water heater. This allows for precise selection of water temperature. For the purposes of data collection, 40 degrees Celsius was used, as it was found to maintain the most stable conditions within the control volume. Here's a top view of the prototype with the lid opened. You can see the PEX tubing, which is used to radiate heat to the environment. The piping path is designed to increase surface area and maximize heat transfer to the control volume. This is a good time to highlight how the volume is insulated, again, with stability in mind with the design.
Now what we'll do is we'll go into the electrical portion of this project. So as we can see here, we have the entire electrical diagram for the project, including the Arduino Uno that was used for data acquisition. Here we'll start with the Arduino Uno. As you can see here, we have it's connected to the computer, which is also connected to an AC wall outlet. The USB port is used for the power/data acquisition. The pins power 5 volts through the temperature sensor module. We have the ground and the pin out for data acquisition. And then what we'll do is we'll now go into this part here. So this is the duct fan and the Honeywell heater, which is connected to the temperature controller, which uses a 110 volt AC wall plug. There's 2 wall plugs on the controller, and then you connect that to the wall outlet. Here we have the solar panels and the power station, which power the water pump. So we have the hot water heater and the water pump. Here we can also see them in real time as well. Here's the Arduino working in real time as well with the data acquisition system. As you can see, it updates it every 100 milliseconds. And yeah, here's the entire project. Here's the data obtained. So here we can see the temperature control modulating itself. During the data acquisition, it was about 55 degrees Fahrenheit and sunny, and the water temperature was set to about 104. So as you can see here, it starts just below 70 degrees. That was due to some of the ambient conditions being a little hot, and it kind of just trends upwards towards 72 degrees. And once it peaks to about 74, the temperature starts modulating itself. This was the highest setting for the air heating during the outdoor trial. And basically, it was able to modulate itself well within bounds. You do have like a little peak above 74 degrees at about 17:30 minutes. But that's fine because it is to be noted that there is an error. And for the most part, the box did maintain its temperature. We would like to give a special thank you to Mr. Professor Jay Mendelson, our project advisor for the semester and the last 2 semesters. He's been a great help for us. We'd also like to express our deep, deep gratitude to the folks at the New York City School Construction Authority. Without them, we wouldn't have been able to do half of the work that we've been able to do the last couple of months. So thank you very much,